In a remote galaxy billions of light years away, a star 100 times more massive than our Sun is dying. For a brief moment, it will unleash more energy than 1,000,000,000,000 suns combined, sending shockwaves across spacetime itself. Tonight, we journey through cosmic forces so extreme they bend reality to their will. We will visit explosions that outshine entire galaxies, black holes that devour light itself, and fundamental forces that hold the very fabric of existence together. Prepare yourselves for a voyage into power beyond imagination. We begin. Deep inside every atom in your body, an invisible war is raging. Protons packed together in the nucleus should tear themselves apart instantly. Their positive charges repel each other with tremendous force, like trying to push two powerful magnets together. Yet somehow they remain locked in place by the strongest force in the universe. The strong nuclear force operates at distances smaller than a single proton, but its power is absolute. Scientists measure it as 100 times stronger than electromagnetism and 100 trillion times stronger than gravity. Think of it this way. If gravity were a whisper, the strong force would be a thunderclap that could shatter mountains. This force works through particles called gluons, which act like invisible chains binding quarks together to form protons and neutrons. The more you try to pull these particles apart, the stronger the force becomes. It is like stretching a rubber band that grows thicker and more resistant with every inch you pull. This bizarre behavior called confinement means you can never isolate a single quark, no matter how much energy you apply. Inside each proton, 3 quarks dance in a prison of pure energy. The gluons that bind them carry the strong force itself, creating a web of interactions so complex that even our most powerful supercomputers struggle to model them. When you try to separate quarks, the energy you add simply creates new quarks and gluons. Like trying to cut a chain only to have it grow new links. The strong force operates on scales so small that a femtometer seems vast. That is 1/4,000,000th of a meter, smaller than anything you could imagine. At these distances, the familiar world of everyday physics breaks down completely. Space and time themselves become uncertain, fluctuating according to the strange rules of quantum mechanics. This force shapes the very building blocks of matter. It determines which atomic nuclei can exist and which cannot. It sets the rate at which stars burn their nuclear fuel. It controls the balance between creation and destruction in the hearts of every star across the cosmic void. Without the strong force, protons would instantly fly apart due to electromagnetic repulsion. Atomic nuclei could not form. Fusion reactions and stellar cores would never begin. The universe would contain nothing but hydrogen atoms and free electrons. Yet, despite its incredible power, the strong force has a fatal weakness. Its reach extends only to the edge of an atomic nucleus about 110 trillionth the width of a human hair. Beyond that microscopic realm, other powers take control. Step into the wider universe where distance means everything and witness what happens when gravity and light collide in the most violent explosions ever detected. Somewhere in the cosmos, a beam of pure energy tears through space at nearly the speed of light. For just 10 seconds, it releases more power than our Sun will produce in its entire 10 billion year lifetime. This is a gamma ray burst, and it represents the most powerful explosion the universe can create. These cosmic titans occur when the most massive stars in existence collapse into black holes. We are talking about stellar giants containing the mass of 20 to 100 suns burning through their nuclear fuel at a rate that would consume our Sun's entire energy supply in just a few million years. When these monsters finally exhaust their fusion reactions, gravity wins the ultimate battle. As the star's core implodes, it fires jets of matter and energy from its poles at 99% the speed of light. The collapsing core creates a newborn black hole surrounded by a disk of superheated material. Magnetic fields twisted and amplified by the collapsed act like cosmic cannons, launching these jets outward with impossible precision. The jets punch through the dying star like bullets through tissue paper, emerging as focused beams of destruction that remain tightly collimated across vast distances. Think of a laser beam that maintains its focus while traveling from Earth to the nearest star. These jets accomplish something similar on scales millions of times larger. A single gamma-ray burst can outshine 1 trillion stars. If you could see gamma rays with your eyes, these explosions would appear brighter than the full moon, even from galaxies billions of light years away. The energy released in seconds exceeds what 10 trillion hydrogen bombs could produce if they exploded every second for the entire age of the universe. The most powerful gamma-ray burst ever detected, nicknamed the boat for brightest of all time, occurred in October 2022. It was so intense that it saturated gamma-ray detectors across the solar system and created detectable changes in Earth's upper atmosphere from a distance of 2 billion light-years. Picture standing on Earth and watching a flashlight beam from Alpha Centauri appear as bright as a car headlight. That gives you a sense of how impossibly powerful these events truly are. The light we detect traveled for billions of years, carrying news of stellar deaths from when the universe was young and stars were more massive and violent than anything we see today. Scientists have detected bursts so distant their light began traveling when the first stars were being born less than 1 billion years after the Big Bang. These ancient beacons give us glimpses of the early cosmos when massive stars lived fast and died violently, seeding space with heavy elements essential for later generations of stars and planets. But compared to what lurks in the darkness between galaxies, even these titans pale in comparison. At the heart of our galaxy sits a monster 4 million times more massive than the Sun. Sagittarius, a star devours everything that ventures too close, from gas clouds to entire star systems. Yet this giant is considered small compared to the true titans of the cosmic deep. Some supermassive black holes contain the mass of 40 billion suns compressed into a region smaller than our solar system. They are like cosmic vacuum cleaners with gravity so intense that nothing, not even light, can escape once it crosses their event horizon. Space and time bend around them like water swirling down a drain, creating distortions that would seem impossible if we did not observe them directly. These gravitational monsters did not grow slowly. The most distant quasars shine from when the universe was less than 1 billion years old, powered by black holes that somehow grew to billions of solar masses in the cosmic equivalent of a few minutes. How they achieved such impossible growth remains one of astronomy's greatest mysteries. Normal stellar evolution simply cannot explain their existence. The leading theory suggests these giants began as massive seeds formed directly from collapsing gas clouds in the early universe. Unlike stellar mass black holes that formed from dying stars, these primordial monsters may have contained hundreds of thousands of solar masses from the moment of their birth. This head start allowed them to grow rapidly by consuming surrounding matter and merging with other black holes. When gas spirals into a supermassive black hole, friction heats it to temperatures of millions of degrees. The material forms an accretion disk that glows brighter than 100 billion stars. The disk rotates so rapidly that matter near the inner edge travels at significant fractions of light speed, experiencing time dilation effects that would stretch seconds into hours for outside observers. The most luminous quasars powered by feeding black holes can be seen from across the observable universe like cosmic lakehouses, broadcasting their presence across billions of light years. They outshine their entire host galaxies, making the combined light of hundreds of billions of stars seem dim by comparison. The most violent black holes launch jets of particles at nearly light speed, creating beams that stretch for hundreds of thousands of light years. These jets carry enough energy to reshape entire galaxies, heating gas clouds to millions of degrees and preventing new stars from forming across vast regions of space. The jets can remain active for millions of years, continuously pumping energy into their surroundings. Recent observations have revealed black holes that seem too massive for their host galaxies, breaking the normal relationships between central black hole mass and galactic properties. These overmassive giants challenge our understanding of how galaxies and their central black holes evolve together. But even these titans bow to forces that operate on scales beyond imagination across 13.88 billion light-years of space. An invisible force is winning a cosmic war. Every second, it pushes galaxies farther apart, stretching the very fabric of spacetime itself, due to the gravitational pull of all the matter within it. Instead, they found the opposite. Space is expanding faster today than it was billions of years ago, as if some invisible hand is pulling everything apart with increasing strength. Think of the universe as a balloon being inflated by an invisible breath. Dark energy is that breath causing every point on the balloon's surface to move away from every other point. Galaxies ride this expanding space like boats on a swelling ocean, powerless to resist the tide that carries them into the cosmic deep. The amount of dark energy in the universe increases as space expands. This seems to violate conservation of energy, one of the most fundamental laws of physics. Yet, observations consistently show that the energy density of dark energy remains constant even as the volume of space grows. Where this extra energy comes from remains completely unknown. Current theories suggest dark energy might be a property of space itself, a kind of cosmic constant that Einstein originally proposed and later called his greatest blunder. Others think it could be a dynamic field that changes over time, or even evidence that our understanding of gravity needs major revision on cosmic scales. The consequences of dark energy are profound and terrifying. In the far future, it will tear apart everything we see. First, galaxy clusters will separate beyond recognition, becoming isolated islands in an ocean of expanding darkness. Then, individual galaxies will lose their ability to hold together against the cosmic expansion. Eventually, even atoms themselves may be stretched apart in what scientists call the Big Rip. Stars will be extinguished. Planets will drift away from their suns. And even the fundamental particles that make up matter will be separated by vast distances. Dark energy, which seems gentle today, will become the universe's final destroyer, unmaking everything that gravity and the other forces worked billions of years to create. Imagine taking a mountain and compressing it down to the size of a sugar cube. The result would still be 1,000 times less dense than a neutron star. These cosmic lighthouses pack the mass of our sun into a sphere just 12 meters wide, creating gravitational fields so intense they warp light itself and bend spacetime into impossible geometries. But gravity is not their most terrifying feature. Neutron stars possess magnetic fields 1 trillion times stronger than Earth's protective magnetosphere. These invisible force fields trap charged particles and accelerate them to nearly the speed of light, creating beams of radiation that sweep across space like cosmic searchlights powered by the fundamental forces of the universe. The magnetic field of a typical neutron star is so powerful it could erase every credit card on Earth from a distance of 600 meters. If you could somehow approach within 000 kilometers, the magnetic force would be strong enough to pull the iron from your blood. The field lines themselves become visible as they trap and channel streams of charged particles into narrow beams. When these magnetized neutron stars spin, they become pulsars, firing beams of radio waves and X-rays with the precision of atomic clocks. Some rotate 600 times per second, faster than a kitchen blender, yet maintain perfect timing that rivals the most accurate timepieces ever built. Each pulse marks another rotation of a stellar corpse spinning in the darkness. The surface of a neutron star is a realm of impossible physics where familiar matter cannot exist. The magnetic field is so strong it stretches atoms into needle-like shapes aligned with the field lines. Normal atomic structure breaks down completely, replaced by exotic forms of matter that exist nowhere else in the universe. Any ordinary matter that falls onto a neutron star's surface would be compressed instantly into a layer just millim thick. The gravity is so intense that a marshmallow dropped from waist height would hit the surface with the force of a hydrogen bomb, releasing more energy than all the explosives used in World War II. Some neutron stars called magnetars have magnetic fields 1,000 times stronger, still approaching the maximum strength allowed by the laws of physics. When these objects experience magnetic quakes, their crusts crack and shift, releasing more energy in 1/10th of a second than our Sun produces in 100,000 years. These magnetic cataclysms create giant flares that can be detected from across the galaxy. The most powerful magnetar flare ever recorded temporarily affected Earth's upper atmosphere from a distance of 50,000 light-year, demonstrating the incredible reach of these stellar remnants. The magnetic field around a magnetar is so intense that it affects the vacuum of space itself, causing it to become birringent like a crystal.